Hello, everyone. I'm Gary Freeland, a senior engineer at TAL Technologies. Our staff of approximately 50 personnel, many of whom are retired military like myself, primarily support the directed energy and space situational awareness research and development communities with quality, high-fidelity, physics-based modeling and simulation software development. But in addition to these important programs, we also develop hardware prototypes and test them. I am pleased to have the opportunity to talk to you today about one of those prototype programs I am very proud of, the Laser Target and Analysis Board, otherwise known as LTAB. This system provides the capability to test laser systems in a real-world environment, and it provides a detailed assessment of the laser system performance. The LTAB program began as a Small Business Innovation and Research, or SBIR Phase 1 program. During my last assignment in the United States Air Force, I supported the research, development, and testing of directed energy-related technologies. One of the greatest challenges I faced in this work was being able to detect and characterize a laser beam propagated through the chaotic atmosphere. When I saw this SBIR needs statement, I was very excited to finally have the opportunity, along with the support of many of my friends and colleagues here at TAL, to work on this important challenge. TAL Technologies has provided significant support to the Air Force Research Laboratory located here at Kirtland Air Force Base. During our 15-plus year history, we have 2 patents that resulted from our SBIR programs. One of those patents, the efficient matrix algorithm, is a method to precisely simulate the propagation of a laser beam through a realistic simulated atmosphere and providing visualizations of the beam's appearance and characteristics at a target plane. This approach, known internally as EMA, provides not only precision propagation, it also greatly accelerates the speed of execution of these simulations over conventional methods. We were able to employ EMA beam propagation techniques to the development of our concept for the Laser Target and Analysis Board. TAL Technologies has an electro-optics laboratory allowing us to rapidly prototype new concepts. We can transition these concepts to field test articles, permitting rapid evaluation and demonstration of revolutionary new solutions to complex problems in the fields of directed energy and military space-related topics. In March of 2017, I was reviewing the latest SBIR solicitations, and the offering November 172-118 immediately caught my eye. The Navy's Advanced Tactical Aircraft Protection Systems Group, NAVAIR's PMA 272 office, needed an approach to test large aircraft infrared countermeasures, or LAIRCM systems, installed on their aircraft, and do so in potentially austere field conditions. I was immediately intrigued by this problem. Trying to see a visible laser beam in daylight after it has been propagated through the atmosphere is difficult enough. Trying to not only detect an infrared or invisible laser in daylight, but also attempting to characterize the power, centroid location, beam shape, and other beam characteristics in field conditions would be extremely challenging. Examples of approaches we have seen to detect lasers outdoors, a couple of which appear on the right of this slide, only provided limited information on the laser being tested. TAL Technologies assembled our team of optical engineers and scientists, and together we came up with an approach that provided exactly what NAVAIR was looking for: a robust, transportable, easily operated system that could provide confident analysis of laser systems undergoing test in realistic field environments. Large Aircraft Infrared Countermeasure systems provide protection for large aircraft against ground-launched anti-aircraft missiles. Typically, these missiles use seekers that look for the infrared radiation emanating from an aircraft's engines and use this heat as a track source to engage the aircraft. When one of these missiles are launched, a countermeasure system must act almost instantaneously, detecting the missile launch and engaging the missile with a laser source to confuse the infrared seeker. The worldwide proliferation of these handheld anti-aircraft systems places large aircraft crews in jeopardy. In fact, the commercial cargo carrier FedEx has petitioned the FAA to permit the installation of large aircraft countermeasure systems on their fleet for this very reason. Protection systems to counter these threats are extremely capable and are typically tested thoroughly prior to delivery to the customer. However, there is a critical need to be able to test these life-saving systems in the environment they must operate in and perform this testing on a regular basis to ensure that they are fully capable of protecting aircrews. In many cases, large military aircraft operate in locations around the world that provide challenging conditions for testing aircraft protection systems. The turbulent atmosphere can very quickly turn the perfection that is a laser beam into a chaotic mess, making it virtually impossible to distinguish the beam's size, shape, and beam centroid. Any solution to this test and verification challenge must permit near real-time assessment of the protection system health and must be flexible enough in design to permit testing of multiple types of aircraft protection systems and their lasers. We began our Phase 1 concept development program by performing simulations of laser beams with characteristics similar to those found in aircraft protection systems. As we perform propagation simulations through all manner of turbulent atmospheres using our in-house subject matter expertise and software tools, it became apparent that our original concept had an unnecessarily large number of laser detectors. Through simulations with our high-fidelity modeling tools, we found that we could exploit certain physical behaviors and characteristics of a propagating laser beam to allow us to perform beam detection and characterization using a very sparse array of detectors in a randomly spaced and arranged manner to fully characterize the beam. Although it is normally assumed that all of the random effects on a laser beam due to the atmosphere are unrelated to each other and can be mathematically summed together, we derived a more accurate approach that provided a much more rigorous estimate of the beam profile and size. This exciting development permitted the design and construction of a transportable prototype that confirmed our modeling. Even more exciting is the fact that this sparse array concept can be applied to virtually any laser type. With our customer, the Naval Surface Warfare Center Crane, located in Indiana, we completed initial test and checkout of the LTAB system. Full evaluation of the detector system, the system control software, and the beam analysis capabilities of the LTAB system were successfully completed in the summer of 2021. With this successful demonstration, it is clear that our LTAB sparse array technology is at a technology readiness level of 6. That is, a successful system demonstration in a relevant environment. At that time, a new program known as the Joint Multispectral Target Board, or JMTB, was initiated. This target board design combines the LTAB sparse detector array system with threat stimulator bricks or modules developed by our subcontractor partner, 1100 Energy. The stimulator bricks provide an authentic-looking threat stimulus to a large aircraft protection system to trigger a laser response from that system. When the aircraft's protection system laser responds, the JMTB's sparse detector array provides full characterization of the laser beam. This analysis, available in near real time, provides beam size, shape, centroid location, power profile, and waveform information. Recognizing the importance of large aircraft protection systems, the Department of Defense has many acquisition programs underway to acquire these critical systems. Just one example are the LAIRCM systems produced by Northrop Grumman. Other large defense contractors are supporting the DoD with aircraft protection systems as well. In addition, foreign aerospace companies that supply capabilities to our NATO allies are building laser-based aircraft protection systems. Major DoD entities responsible for military aviation system test and evaluation have recognized the fact that there is a capability shortfall in large aircraft protection system and other laser system test and evaluation. Also identified is the need to test these systems in the environment in which they operate. Finally, the ability to exercise these protection systems in a flight condition would provide a much-needed, realistic training environment for operational aircrews. Because of these requirements, TAL Technologies was awarded a Phase 2 SBIR enhancement, allowing us to begin preliminary design of the JMTB, a system that could address these testing capability shortfalls. Our joint multispectral target board system concept provides a transportable, completely self-contained laser measurement and test facility. The system incorporates TAL's sparse array laser characterization system, along with the stimulator panels mentioned earlier, and mounts this system on an azimuth elevation gimbal. The gimbal provides the ability to point the target board in an aircraft in flight, and then stimulating the aircraft's countermeasure system, producing a laser response that can be received and analyzed by the sparse array. If the JMTB system is located on a test range, radar, time, space, and position information, or TISP data, can be used to drive the gimbal. The Integrated Operations Control Room and Power Generator permit testing of laser systems at virtually any location. A JMTB system could be used at a contractor facility to test newly integrated countermeasure systems prior to delivery to the customer. I have personally spent hundreds of hours in the field testing laser systems. In many cases, this expensive testing could have been greatly accelerated by the ability to analyze laser beam characteristics quickly and accurately, permitting the quick resolution of problems causing beam misalignments and power changes. Detailed laser testing is difficult enough in a controlled laboratory environment. When testing an invisible infrared laser beam, the detection and analysis challenge is even greater. When sunlight, wind, extreme temperatures, and other manifestations of Mother Nature threaten laser testing, the TAL Sparse Array Laser Target and Analysis Board system can support testing where other target board approaches fail. The LTAB system provides complete transportability, ease of setup, intuitive user interfaces, and an adaptable design to meet just about any laser testing challenge. Our approach uses a sparse array of detectors to perform direct detection of the incoming laser beam. Other approaches utilize cameras to image the incoming beam on a screen. This approach lacks the ability to characterize the beam at high speed due to the frame rate limitations of the imaging camera. The imaging approach also negates the ability to track airborne laser systems for in situ testing. TAL's LTAB system provides high-speed data collection and storage for additional data analysis, and the control software is well documented, permitting modification and the addition of enhancements. Given the significant capability of our laser target board, we believe there are opportunities for partnership. NavAir and the Redstone Test Center have already identified major shortfalls in outdoor in situ laser system testing. The TAL Laser Target Board provides a complete, cost-effective approach to laser system test and verification that currently doesn't exist. Opportunities to partner with our large defense contractor friends could yield integrated test capabilities to support large aircraft countermeasure acquisition programs. The LTAB system could also facilitate the testing required to validate countermeasure system modifications to meet changes in threat systems. Finally, DoD's directed energy research and development community could greatly benefit from having a maintainable, adaptable, and mobile system to support directed energy system concept testing. If you have a laser system that requires testing and evaluation in an outdoor, real-world environment, the TAL Technologies Laser Target and Analysis Board can be the solution to help you accomplish your mission. I greatly appreciate your time today, and I hope you will contact us with your laser testing or modeling and simulation needs. We stand ready to support you. We at TAL Technologies would like to acknowledge the valued support of the United States Navy and our technical point of contact, Mr. Matt Mullins, and the important guidance and support of the Navy Small Business Transition Program, specifically Mr. Ian Roth and Mr. James Bulling. If you would like to discuss this project or any other topics that we might be able to assist you with, please give us a call at the above contact numbers. We would love to talk to you. Take care.